The Riemann hypothesis is called the holy grail of mathematics. But ironically, Riemann himself didn't see it as important. It wasn't his goal. So, what was Riemann really trying to understand? Our story begins with this function called pi of x. It counts how many prime numbers are less than or equal to x. Mathematicians try to describe this staircase with a simple formula. The first major insight came from Gauss. Looking at data, he noticed and proposed an integral function, Li of x. It works extremely well. But pi x jumps while Lix flows smoothly. That small difference is exactly where Riemann stepped in. Riemann wanted to describe these tiny fluctuations, but he didn't trace primes directly. Instead, he turned to a completely different world, zeta function. He explored the zeta function deeply and introduced a new way to count primes, a function called J of x. It counts not only primes, but also prime powers in a weighted way. Each prime p contributes 1, but p squared contributes 1/2, p cubed contributes 1/3, and so on. Surprisingly, the graph of Jx turns out to be very close to the graph of pi x. And then Riemann discovered that Jx could be written as an explicit formula. Now, compare the values of pi x, Jx, and Lix. Jx is far more powerful than Lix. But there was still one final step left. Jx is not exactly pi x, because it also counts prime powers. So Riemann needed a way to recover the true number of primes. This is done through the inversion formula. This leads to what is known as Riemann's prime counting function R of x. Rx is extremely close to pi x. Their graphs are nearly indistinguishable. Riemann had achieved his original goal.